So you can see here, when you give a step signal, when you give a signal like this, it will increase, oscillate, and then settle down to some constant value after a long time. Okay, so all the parameters, rise time, the peak time at which the peak occurs, what is the maximum settling time, everything is shown in the figure. And the frequency parameters you see, so this is going to be a constant thing, and it is going to reduce. So this is the peak frequency, and 3 dB cutoff point you take, you get omega h. So this is the first order system. We have the parameters are going to be very, very simple. Now second order system, this is a transfer function, s square by omega n square plus 2 xi s by omega n plus 1 whole inverse. And same way rise time is going to be same. And the p naught, the maximum value of the overshoot, that is given here, 1 plus e power minus pi xi by root of 1 minus I square. Tp, the time at which peak occurs, it is given here. Settling time is also given here. And the delay is given here. The maximum overshoot value is given. And the xi value is less than 1 by root 2. And omega p, the peak frequency is given. And what is omega? 3 dB cutoff frequency is given. So all the formulas are given. So the rise time of second order system is somewhat dependent on damping ratio. That xi, whatever is denoted here, right? So that xi is going to be called as the damping ratio. The peak overshoot cannot exceed 100%. So it will be less than 100% only. And the time at which the peak overshoot occurs is going to be called as Tp. And we have got the expression for Tp. And P naught is the maximum amplitude which occurs in the time domain. And finally, we have this delay, the epsilon. What is the delay in time when you give the input? So that is going to be epsilon. And finally, the frequency response, we find two frequencies. One is the frequency at which peak occurs, and other is the frequency at which 3 dB difference is there. So that is called as omega p and omega h. And you have omega n, which is called as a natural undamped frequency of the system. So which is the natural frequency that the system is going to resonate. So what is the thumb rule we are going to fix for stability? To bring phase margin into discussion, we are going to make a lot of assumptions, but there is no relation between phase margin and damping ratio. So whatever parameters we have seen, gain margin, phase margin, root locus, and now the time domain parameter, there is no physical relationship between any of the parameters. The stable system, more or less, we model the stable systems using first order or second order systems only, because more the number of order we consider, the systems become complex, and the parameters are going to be very difficult to analyze using mathematical models. So we'll try to fit whatever system we are going to analyze using a first order or second order system only. Specifically, that too, we are going to assume a two-pole system with pure scalar feedback. So we are going to limit the number of poles in our system to 2. So that we have all the formulas in hand, and I can use the relationship, and I can find what is the required rise time I should have, what is the required settling time I should have, so I can design that. But we can still derive the relation between damping ratio and phase margin. So I can do that, and that's done here. And approximately you can say it is damping ratio is 5m by 100. 5m is the phase margin in degrees, and xi is going to be damping ratio, it is 5m by 100. So 5, and that is what is given here. This relationship is accurately for 15% tolerance. So if the phase margin is less than 70 degrees, then you have 15% accuracy. So it is better to have 10%. If the tolerance is less than 10%, you can even have more accuracy, and the answer, the damping ratio will be got in an even more easier way. And even same way, I can relate between maximum overshoot and the phase margin using this relation. Okay, again, phase margin is given in degrees, and I can find P naught, which is going to be the peak at which the peak value of the signal. And I can even find what is the relation between the maximum frequency picking and phase margin. So why I'm relating everything with respect to phase margin is because compared to gain margin and phase margin, computing phase margin is very simple, because at phase margin the gain value will be equal to 1, correct? It will be equal to unity. So computing phase margin is going to be very, very easy for me. So this system is accurate up to 1% for a phase margin of 55 degrees. So it is going to be accurate. With these approximation, it is simple to estimate what phase margin is required when time domain or frequency domain parameter is required for us. Also, all these are only for two-pole system. So if the number of poles are going to increase, then you have to again go for different mathematical calculations. You cannot use these formulas because they are specifically designed only for two-pole and one-pole system.